So now that we've defined these partial molar quantities, we can use them in many of the same thermodynamic equations that we've derived up to this point for pure substances. So for example, we define the Gibbs energy as G equals H minus Ts. We can take a derivative with respect to the number of moles of substance J in a solution, and I'm leaving off the fact that we're holding temperature and pressure and et cetera, constant. But we can write that's equal to dg dnj. Now I'll add all these other things that are being held constant. I'm not going to write them in all the other ones. But we'll also have dh, dnj, keeping tp, et cetera, constant, minus t times ds, dnj, holding everything else constant. And we would get a second term that would go to 0 because t is held constant, so that wouldn't make any sense. And so this becomes that this is the partial molar Gibbs energy is equal to the partial molar enthalpy minus the temperature times the partial molar entropy, right? We can write this, we've just written everything as partial molar quantities instead of molar quantities. We can also go a step further, right? If we take a, if we want to think about an analogy to dg equals minus sdt plus vdp, we can rewrite this in terms of partial molar quantities. So the partial molar Gibbs energy, just as a reminder, this is the same as what we call the chemical potential of substance J. So we can say that d mu J is equal to minus s bar J dt plus v bar J dp, right? We can just rewrite everything in terms of, just like for a pure substance, but now just everything's in terms of partial molar quantities. Right, so this version is for a pure substance. This version is for a mixture. Okay, and now starting from this second equation, we can derive, well, not exactly from this equation, but we can derive the Gibbs-Duhem equation, which allows us to relate partial molar Gibbs energies or chemical potentials to each other in our system. So we can say that, okay, at constant T and P, we have dg is equal to, I keep writing I instead of 1, mu1 dn1 plus mu2 dn2 plus n1 d mu1 plus n2 d mu2. So this is this is taking the derivative of this equation. G equals n1 mu1 plus n2 mu2. Right, so if we just take the derivative, we get this. And so we have two, right, we have the terms where we take the derivative of n and the terms where we take the derivative of mu, right? It's just using the product rule of derivatives. Okay, and then we can subtract this, subtract the equation that dg is equal to mu1 dn1 plus mu2 dn2. We showed this earlier, so subtract this from this equation up here. There's lots of g's and mu's. What this lets us do is we can, we're going to cancel these terms over here. We're also going to cancel with the dg. So we'll get something equal to 0. So we'll have 0 is equal to what's left over, right? These terms, which I'll put in green on the right over here. All right, so we'll have n1 d mu1 plus n2 d mu2. For those of you who like Pokemon, I keep saying Mewtwo, so maybe I'm a little old for that. But and then this is what we call the Gibbs-Duhem equation, right? This right here, usually rewritten so that we don't have a 0. So we just rearrange this and say that, or rewrite this in terms of partial, the mole fractions, right? So if we divide everything by n1 plus n2, then we get that x1, where x1 is the mole fraction defined as n1 over n1 plus n2, maybe you haven't thought about this unit for a while. We're going to see this quite a bit in this particular chapter. X1 d mu1 plus x2 d mu2 is equal to 0. This is usually the way we write the Gibbs-Duhem equation. Now, why is this useful? This is useful because if we know one chemical potential of one component, right? If we know mu1, maybe an equation that describes mu1, it lets us find mu2 as a function of the mole fraction in our substance. And so this gives us a way to relate chemical potentials to each other. So if we know the chemical potential of one component, we can figure out the chemical potential of another component. In the next video, we'll show a specific example of that. Say we can write mu2 in a specific way. How would that then affect mu1?